definition of static versus instance methods, and then we will talk about why recursion works and why we can think about how we can sort of build confidence that when you are writing recursive methods, that the recursive methods that you are writing are both correct and will work for a variety of cases. Before we do that, I'm going to once again nail down the difference between static and instance methods. This comes up a lot in the slides, which is usually a good indication that it will come up on an exam. So it's important to note the difference. Static versus instance methods are important, allegedly. So static methods, as you might recall, are able to be called in two different contexts. The main draw of a static method is that you do not need an object on which to call the static method. It can be called from a static context, either from the file in which it is defined, from file defined, or as is the case with most static methods that you will import via a package, you can call it via a class by providing it with the class name beforehand. So from another class. Instance methods, on the other hand, have to be called on an instance of an object. Instance of an object. So, for example, the increment, decrement methods have to be called on an instance of a natural number because it doesn't make sense to just increment a natural number, or it doesn't make sense to increment something that doesn't exist. If you just called an increment method and then didn't pass anything in, it would be kind of confusing as to what you were trying to increment. Most of the time, you can make instance methods into static methods. The main difference between the two is you extract out one of the distinguished formal parameters from the static method to become the object on which you are calling the instance method. So, for example, you could have an increment method which took in a natural number temp and just called temp.increment. And because a natural number is a mutable reference type, the number would be different afterwards. What you're essentially doing when you're making an instance method is you're taking that temp natural number and you're moving it out towards the front and then dropping it from the list of distinguished formal parameters. So it just becomes the distinguished formal parameter for this. Some common features between both of them. I forgot to start recording. That's not a common feature of methods. That's just something I forgot to do. Oh, wait, no, I did start recording. Okay. Both may have formal parameters of any types. They may return any type or nothing, which remember are void methods, and then may be public or private. Public or private, as an aside, simply tells you which context you can call the method in. So if you have two files like this, one called foo.java, and then another called foo2.java. If a method, a static method, is public, then that means that it can be called from the context of another Java file, as long as you import the Java, the foo class. Private means that it can only be called within its own class. And this is important because oftentimes you don't want your methods or any information contained within those methods, such as variables, to be able to be called from other contexts, from other files, because people are secretive about their data, especially large companies. And may compute the same things. So again, increment could be technically an instance method. Instance method could technically be a static method. It all just depends on where you put the parameters and what you want from the parameters. Arguments are passed to all calls using the same parameter passing mechanism. So this is like separate, so let's draw like a thing. But remember, parameters can either be passed by value, if they are a primitive type, like integer, double, Boolean, or they can be passed by reference, which is like any object type. So natural number, XML tree, so. You go to define the method, you tell Java what the user should pass in as the parameters, and then when that function is actually called, those types, the same types of parameters need to be passed in. Call by copying or call by value. Same thing. Call by copying is passed by reference. Call by value is passed by value. They're just other names for them. Okay, static methods are declared with the keyword static. So that's really the keyword that you have to add, which just tells Java like, hey, this is going to be a static method. It should be defined and called in a static via a static context. That's what I'm looking for. So suppose power is a static method declared in the natural number static ops or operations class. This is what a declaration might look like. The entire thing is called the method header, just the name of the function, and then the parameters is the method signature. As with all signatures, mostly it is unique. So you cannot have another power method named power that takes in a natural number n and an integer p, or just a natural number in general and an integer. You could have another method called power2, which takes in a natural number and an integer. You could have another method called power, which takes in an integer and an integer. But you cannot have another method called power, which takes in a natural number and an integer. You could have a class which inherits or extends the natural number static ops class and then overrides this power implementation. But that is overriding and not overloading, which is a different thing in which you provide different argument types or a different name with the same arguments. Overloading is the same name for a method, but a different number of parameters or types of parameters. So you could have a power method that takes in 3 arguments, a natural number, an integer, and then another integer for some reason, and that would be an example of overloading the method. Overriding would be you have another class which extends the natural number static ops, but then overloads or overrides the power method to provide a different implementation. We talked about that last week at some point, so there's a lecture on it if you're confused. Okay. Whether it is public or private is unrelated to whether or not it's a static method or an instance method. Instance methods can also be public or private. So these are general. Public and private has to be, I think, defined for all methods, or it should be. Static methods are called without what is known as a receiver. So called on an instance of an object, that's called the receiver. The receiver is just the object on which is receiving whatever the function call is. So call to power from within the class, natural number extra ops might look like this. So when you're actually in the class in which the function is defined, so power, you don't have to tell Java which class you're calling the function from because you're already in the class on which you have defined the method. This is different from if you want to call it from another class. So if we wanted to call it from foo2.java, you would have to call foo.power, which tells Java, hey, in the foo class, there is a public static method called power that I want you to run. And so Java will go to the foo class, go to the power method. That's how it will know which implementation to use. And so they have another example there, the power class or the power method. And then if you're calling it from outside the natural number extra ops class, you qualify it with the name of the class. So natural number extra ops, essentially the same as putting foo.power. Questions so far? Awesome. Compare this to instance methods, which are declared without the keyword static. And so again, same method, power p or power, which takes in an integer p. You'll notice that the difference between these two is that the static method takes in a natural number n, but the instance method does not. And that's because we've moved this natural number n out to the front of the method, and it's serving as the receiver. So you're still passing in 2 arguments. Just one of them has become what's known as the distinguished formal parameter, this. And this just represents the natural number on which you are calling the method. We call it this because, again, we don't know what the name of the natural number on which we're going to call the method is. We don't know if it's going to be temp, temp2, and so we just refer to it as this. Again, public or private, doesn't matter whether it's in static or an instance method. Why is there only one formal parameter? The other parameter is this, which is implicit because it's an instance method. So you will always have access to what is known as this. When you're writing instance methods and you want to refer to the object on which the user is calling a method, you refer to it as this. So if you're doing increments, I don't know, you wanted to have an implementation that was just this dot add new natural number 1, because that's a way that you could implement an increment method. In order to talk about the natural number on which it's called, you refer to it as this within the method body. And then when you call increment on a natural number such as temp, temp takes the place of this in the method body. Essentially, it's the same as if you have a natural number temp, which you've added to the method signature of a static method, you call it temp dot or temp dot add your natural number. All right. Instance methods called without a receiver. So a call might look like this: m dot powered k, where m is the natural number on which you're calling the power method, and k is the integer to which you want to raise. Okay, can you tell from a method declaration whether it is a static or an instance method? So yeah, that's a good question. How do you know whether it is an instance or a static method? Because technically, you could be calling the dot bar method from the foo class and passing in 3 parameters, or you could be within your own class and calling bar on a foo object that you've defined in an instance method. So really, it's difficult to tell the difference, but make sure that you know which methods you're writing. It's not always easy or ambiguous, or it's pretty ambiguous as to whether or not you're calling an instance method on an object, an instance method that you've defined in the class on an object, or whether you're calling a static method from another class, a static method from another class. End of sentence. A good way to tell is you can look at your import statements. You can see which classes you're importing from. And then also, it's probably not a good idea to name classes something that a variable name could be named. Like nobody's going to name their natural number extra ops. And oftentimes when you're defining classes, we always follow a different naming case. So you always use capital letters as opposed to camel case, which is usually the case for methods. Okay. So I have 2 kinds of methods. If you can simply extract out one of the formal parameters and make it an instance method. One of the big reasons is polymorphism. So it allows you to have multiple implementations of the same method. That goes back to what we talked about on sometime last week, where if you override a method, then you can provide a different implementation. And yeah. Instance method that has exactly the same functional behavior as a static method simply distinguishes one formal parameter by placing it out front. It means that there must be a receiver of a call to that method. This is why an instance method seems to have one less formal parameter. Why the increment method seems to have no formal parameters, while this one has 1, is because we've extracted out the formal parameter to the front. And then recall that polymorphism is the mechanism that selects the method body to be executed based on the dynamic type or object type of the receiver. So another thing about instance methods is depending on which implementation you're using of a class, say natural number 2 versus natural number 1L, might have different implementations of the add method or the increment method. And so in order to distinguish between the 2, it must be an instance method. All right. So implementations. Although in Java, as far as this class is concerned, you can declare a static method in an interface. You are also required to provide an implementation or a method body. This limitation, along with the flexibility added by polymorphism, is a good reason to generally prefer instance methods, because we typically never want to actually provide method bodies in interfaces, because it completely violates the idea of design by contract, where the interface is only in charge of describing behavior and not providing actual implementations, and then the classes are in charge of actually providing the implementations. Since in Java 8, which is the methodology that we use for this class, you cannot define static methods in an interface without also providing a body. It's imperative that you always try to make things instance methods. Again, interfaces are meant to be used for contracts only. Client view and including implementation code breaks the clean separation between the client view and the implementer view. We don't ever want to provide implementations in an interface because it just goes against everything we've learned about design by contract and separating out what you need to do. Okay, implementations, I guess a review or an overview. The variables in scope in a static method's body are its formal parameters. So anything that's defined within the method signature as a formal parameter. And then the variables in scope in an instance method body are the explicit formal parameters, which are any additional parameters you add to an instance method's method header, as well as the implicit formal parameter this, which is the object on which you're calling the method. Object on which you're calling the method. The bodies do not differ otherwise. Okay. Questions on static versus instance methods. I think that's like the third time we've gone over them, so hopefully it's locked in now. Okay. Back to recursion. But first I'm going to erase this. Is that okay? So a few lectures ago, we talked about what recursion is and how to write recursive methods. And one of the strategies that we talked about was pretending that you had an implementation of the method that you're trying to work that only works on smaller instances of the problem. So if you're trying to write a reverse string recursive method, pretending that there is a reverse string method in this class called free lunch that you can use to write the rest of your method. And as long as you do that and you make the problem smaller, and your other implementation works, you're able to write a recursive method pretty fluidly. And you include the three things that are required for all recursive methods, which are a base case, a point at which to stop, a way to make the problem smaller, because again, when we're using free lunch, it only works on a problem that is smaller, and then a recursive call, because what good is a recursive method without a recursive call? It's not a recursive method, it's just a static method. There's your steps. So that's how you should think about recursion so that you can use it to develop elegant recursive solutions. Answer, pretend that there's a free lunch method that has the same contract, but only works for smaller problems. The question we are now going to consider today is why these recursive methods work. So when you're writing recursive methods, sort of what are some strategies that you can use to prove that the method that you've written actually works? Why is it supposed to work? A question we won't consider now, but we'll consider after spring break is how recursive methods work. We will come back to it. Again, if you start by insisting on knowing the answer, you may never fully be capable of developing elegant recursive solutions. And here's the example that we brought up the first time that we learned recursion was the reverse string method, where if the string is length 0, you just return S because an empty string reverse is just empty string. Else, you chop off the first character, you reverse the rest of it, and then you add that first character onto the end of the reverse string. Because we noted that if you have a word like spot, and you chop off the first letter, and then you reverse what's left, and then you add that first letter back onto the end, it is a reversal of the string. And since we have this free lunch method, which reverses the string for us, this is pretty trivial to do. We just chop off the first character, reverse what's left using this method, which already reverses the string, and then add it back onto the end. And then you return the result. This is a slight modification where instead of just defining the result, you just return the result. This is also a bad implementation because it uses multiple return statements. A good way to fix this, I don't know if they talk about it in this lecture, but you can just have a string called return string. Red string, which is initially set to the empty string, and then you cut out everything. Like if s.length is not equal to 0, then you do the whole chop off the first character, reverse it, add the first character onto the end. And if the character is the empty string, it will skip over that if loop, do everything else normally, and then you just return string, red string. And then in the case that it is the empty string, it will just, I spelled it wrong, didn't I? SRT, STR. In the case that it is the empty string, it will skip over this if statement, it'll skip over the process of recursively calling the method, chopping off the first character, and it will just return the empty string. So that's how you could do it if you don't want to use multiple return statements. And you should, because multiple return statements is illegal in this class. Okay. So in terms of actually checking to see whether or not checking, but proving that your recursive methods work and work elegantly, we're going to be using a confidence building approach. This actually is a very good way to make sure that the recursive method that you have written is correct. Essentially, what you do is you start with the smallest possible value that the recursive method could be called on. So look at the contracts for this, or just think technically, like with a string method, the smallest is going to be the empty string. With a natural number, the smallest thing that you can call it on is going to be 0. And if you can prove that your recursive method works for the smallest possible metric, and then you can prove that because it works for the smallest possible metric, it works for the next one up, so a string of length 1. And then because it works for a string of length 1, it should work for a string of length 2, and so on and so forth. Eventually, you get to the point where you can say, not 100% confidently, but you can say, I'm pretty sure that this recursive method works. This is similar to when we're going to talk about testing your code, which we do at the end of the class, where you can never be 100% sure that a method that you write is correct. You can only be pretty sure. And so, yeah, that's what we're going to be talking about today. So first, consider the smallest problem according to that metric. In this example, there's exactly one smallest problem. The length of the string equals 0, or s is the empty string. If you can convince yourself that it works correctly for that one, then you can extrapolate it up to working for a string of length 1, a string of length 2, and so on and so forth. And the reason that you can do that is because, well, we'll get into it. I don't want to spoil it too bad. All right. Possibly the most fun tracing table that we will ever have is calling a reverse string method on a string of empty length. What's going to happen is you call the reverse string method. If s.length equals 0, return s. S.length is equals 0, and so we return s. So that's the smallest case on which you can call the reverse string method. Does it work? Well, the empty string reversed is just, again, the empty string. So big thumbs up. Our recursive method works for a string of length 0. Hallelujah. Now we consider the next smallest problem according to that metric, and that would be a string of length 1. So just to keep track, we know that it works for a string of length 0. Now we're going to check if it works for a string of length 1. We don't know. Now, again, with the tracing table, if s.length equals 0, that is not the case because we're calling on a string of length x. So what we have to do is we have to chop off everything after the first character, which is chop off the first character and then reverse what the rest of the string is. So we chop off the first character, which is x, and then the rest of the string is the empty string. So we call a reverse string on that empty string, and we know that it works, or that the reverse method works on an empty string because we just tested it. And so we can ensure that what gets returned to us is the reversal of the empty string, which again is just the empty string. And then we do the same thing. We add x back on to the end of the empty string. We return that. So is x reversed x? Yes. So it works for a string length 1. And now we move on to the next case, a string of length 2. And we can use the fact that we know that it works for a string of length 1, which uses the fact that it works for a string of length 0 to prove that it works for a string of length 2. How do we know that the recursive call does? We just convinced ourselves because we just proved that it works for the smallest case. In this case, that returns the value of x. Since reverse sub is the empty string and s is x, this satisfies the post condition that the reverse string is x. So now we know that it works for a string of length 1. The next smallest problem is a string of length 2. So we can use, I forget what they use here. So they use the string p and u. So we start with a string of length 2, which is p and u. Since it's not equal to 0, what we do is we chop off the first character. So sub becomes just u. And then we call reverse string on that. It is a string of length 1. So we know that it will actually return to us the correct answer, which is just u. So reverse sub is now u, proved in the last iteration, and then we return reverse sub plus the character at string 0, which is just p. So the resulting string is just u, p, which astute viewers may know is the reversal of the string p, u. So it works for a string of length 2. How do we know that reversing a string of length 1 works? Because we just proved it. In this case, it returns a value up, which is a reversal of the string pu. So now we know that it works for a string of length 2. Now we consider the next smallest problem. I think this is the last one we do, don't worry. But since we know that it works for a string of length 2, the last one that we really need to check is a string of length 3. And so we can use the string OSU, I believe that they use. So OSU is the string which we pass in. It is not of length 0. And so what we do is we chop off the first character, and then sub is the last 2 characters. So S and U. And then we call reverse string on sub, which is S and U. And since we know that it works for a string of length 2, what gets returned to us in reverse sub is US. Then we add the first character onto the end of it and return it. So what gets returned to us is USO, which is OSU backwards. And again, we know that it works for a string of length 2 because we just checked it. So now we could keep going all the way up to strings of length 100, but unfortunately, we only have 55 minutes in today's class. So we know that it works for a string of length 3, and so on. You should see that the reasoning could continue long enough to reach a finite integer length with the conclusion that the value of the code works for any string of value s. But s must have a finite length because you can't store infinite values. So we say that it probably works for most things. This is a technique that you will learn. Maybe you already have. But there's a class called 3345, which gets into mathematical proofs. You'll learn about proof by induction. This is essentially proof by induction. You prove a base case or a smallest case, which in this case that it works for a string of length 0. And then you prove that because it works for a string of length 0, it should work for a string of length, any length past that, a string of length 1. Because it works for a string of length 1, it should work for a string of length 2, and so on and so forth. Recursion and induction are entirely parallel concepts. Yeah.
Can we technically, are we doing this for the example, or could you could technically just reverse string OSU and it will give you USO?
Yeah, if you have the correct, are you saying like use a like a built-in reverse string method? You could, but if we say write a recursive method that reverses a string and then you just call a reverse string method, that's cheating.
Okay, so it's like
Yeah.
we're kind of like learning recursion with like a simple.
Yeah, it's a simple example.
Cool.
There are way easier ways to reverse a string,
Okay.
but this is a way that is conducive to learning about recursion.
Okay, cool.
Essentially. So make sure when you're writing recursive methods that you're actually writing recursive methods and not just writing iterative methods, because you will get no points. Okay. Another formal pref technique, one which we won't use because it's a lot more confusing, but gets brought up because, I don't know, I didn't make the slides, is proof by contradiction, which is where you assume that it doesn't work and then prove that that can't be true because of things that you know. So the example they give is that you suppose that the code does not work for some s, then there must be some shortest s for which it does not work. So assume that the length of that is n. Now let's show that this assumption leads to this conclusion that the code must not work for some string of length n-1. This is a contradiction. Hence, there cannot be any such s for which the code does not work. How this manifests is you could say like, if we think that it doesn't work for string of length OSU, then we must prove that a string of length 3, if a string of length 3 doesn't work, and there must be some smaller version of it that does not work. And it's not 2, and it's not 1, and it's not 0. So technically it has to work for a string of length 3. This is a far more confusing way of thinking about things. So if you want to, you can just forget about proof by contradiction because it doesn't ever come up again. Some people find this kind of easier to understand than induction, but it does not seem to have a simplified intuitive basis like induction does. Induction is the main way in which, if you're wondering whether or not your recursive method works, you should use to test it. So for example that I brought up, I think last week about testing whether or not I'm going to forget the name again. Same forwards and backwards. Anagram? Palindrome. Testing whether a string is a palindrome. You would test whether it works on a string of length 1, 0, 1, 2, 3, and so on. And that's a good way to prove to yourself that your recursive method has worked. All right, that's the reverse string example. Now we can get into one more example, which is the increment method. If you're writing a recursive increment method, how do you know that it's actually working correctly? Well, you do the same thing. In this case, the smallest value on which you can call an increment method is just a natural number, which I'm going to call n, which points to 0. So let's go through the same approach that we used last time, where we test whether or not a natural number of 0 or of value 0 works. Okay. So does it work for 0? Well, let's see. So we say the ones digit is whatever n dot divide by 10 is. So ones digit, I'm going to abbreviate to OD, is just 0. Ones digit plus plus, okay, 1. If ones digit is 10, it's not, we skip over it, and then we call n dot multiply by 10, and then add the ones digit. Is 0 plus 1, 1? Thank you. Correct. So it works for a natural number of value 0. Okay, now we can try 1. Same thing happens. Oh, it's already written there. Ones digit is 1. We add 1 to the ones digit integer, becomes 2. Ones digit is not equal to 10, and so we call n dot multiply by 10 and add the ones digit, n becomes 2. And that's what gets returned. Is 1 plus 1 2?
Oh yeah.
Beautiful. Correct. Probably the hardest question I will ever ask. Now, we could do this all the way up until we get to 9, but that seems pedantic. So the next interesting value that we really should worry about is whether it works for an integer of 9 or a natural number of value 9, because that's where things get a little bit hazy. Where things get more interesting, I'll say. So if we have a natural number with value 9, we call n dot divided by 10. So n becomes 0, so divided by 10. OD becomes, or ones digit becomes 9. We increment it, so it becomes 10. Now we say if ones digit equals 10, is the case. So we set ones digit back to 0, and then we increment n. And we know that from our previous example that increment actually works when you call it recursively. So this becomes 1. And then we call n dot multiply by 10 and then add the ones digit. So this becomes 10. And is 9 plus 10 is 9 plus 1 10? Yes. That works. We could do one more example. Example of, say, 99, where we call ones digit dot divide by 10. Ones digit becomes 9, n becomes 9. We add 1 to ones digit, it becomes 10. And then, since it's equal to 10, we call, we set it back down to 0. And we call increment on whatever is left. We just proved that increment on a value of 9 works, and it returns what it actually should, which is 10. And now we call n dot multiply by 10 and add the ones digit back. So it becomes 100. Now we've proven that it works for 99 as well. So you build up confidence in the fact that your recursive method works because it works on the smallest case, and then it works on maybe a slightly larger case. And because it works on that slightly larger case, it works for a larger and larger and larger case. And that is how you know that your recursive methods are actually working correctly. And then this is just going through what we just did. Next smallest is a problem of 1, so on and so forth. It takes 9 steps before anything interesting happens. And then here is the conclusion. The purpose of the confidence building method is, as its name suggests, to give you confidence that the code works. A nice feature is that it suggests some test cases you should decide to run the code on the computer rather than tracing it manually. So also when we get to testing, you'll have to make what are known as test cases, which put your methods, your static and instance methods, essentially through the ringer to prove whether or not it's actually correct. This method will give you some sample test cases on which you should call your methods if you want to prove that they work correctly. However, you still may need to trace it, albeit perhaps only mentally, in order to have the written code in the first place. The biggest place in which this lecture is going to come in handy is when you are writing recursive methods on your midterms and finals. I would be, again, very surprised if you got to the second midterm or the final and you did not have to write a recursive method. So after you have written your recursive method, try it on the smallest case, try it on the second smallest case, so on and so forth. And if you can prove that it works to yourself on those smallest cases, and because it works on the smallest case, and it works on a slightly larger case and a slightly larger case, you will be in a good spot for making sure that your recursive method actually works. Okay. You might be surprised how many people who should know better seem not to have noticed this rather obvious conclusion that you still have to trace your code. You should still test it. I would say put it through a few testing examples, but start with always the smallest case. Because it works for the smallest case, and then it works for the second smallest case. Probably works for larger cases. Okay, any questions? We have like 15 minutes. I'm on payroll for 15 minutes, so. All right. Gift of time, you guys can get out of here early on this lovely Tuesday morning. I'll put the attendance code back up. Well, is the question. I have a question. Yeah.
So when we gotta import, I don't know where we gotta import the utilities reporter for like the fatal error by.
Yeah.
Do we gotta create like a method for it, or can we just call a fatal error?
There should be a.
Because when I clicked it, when I went to the API, that's what it said. But I just wanted to double
There
check.
should be a reporter class. Hold on. Which lab is this?
Oh, this is the project 7.
Project 7. Jeez, can't get to my. Components.utilities.reporter. So you import components.utilities.reporter, and then you should just be able to use this assert or fatal error to console. So go to your import statements and do, actually it should autofill. Type import. Components dot utilities dot reporter. All right, and then go down
And
to
when I save it, it erases.
it deletes it.
Yeah.
Why?
Every time I say it.
That's so interesting. Why? Maybe because you're not using it. What do you save it to? Go down to like. If I guess if you don't use a package and then you import it and then you save, Java goes through and removes it, which is a stupid way of doing things, but yeah. So you use the built-in static method fatal error to console from the reporter class. Like that.
All right.
Thank you. Thank
So for instance methods,
Mhm.
when we're working with this, like, do we have to like declare it as some specific type of variable?
No, so if it is, so anytime you write an instance method, you'll be writing it in a class. And then the type of object on which you're calling the instance method is just whatever class you're in. So if you're writing an instance method in a natural number class, you just have to call it on an instance of a natural number. If you're writing it in an XML tree class, it's just an XML tree that the object is. Does that make sense?
Yeah.
Okay.
Thank you.
Yeah.